Hi and a very good day. So in this video session, I will continue discuss on box Jenkins method using R programming, which is now I will use palm oil production example. Alright. Again, this data set will be given and make sure that upon reading the data set, it is successfully read by your R. Okay, so here if you if you have any problem regarding reading the data set, make sure that you ask for you ask for support. Okay, right, so here again let's take a look at the data set. Okay, so here we will use the palm oil production example, and the thing that we are interested to investigate is the palm oil production tons here. Okay, you can refer to your data set, make sure that it is successfully read by R. Okay, so now this is actually just some additional argument. The most important part is when you want to plot this kind of when you want to plot the variable. Okay, the function that you will use is the plot function. Okay, now here I already define the object as a time series object, name palmoil.ts. Okay, so this ts function here is to define the object as time series. Okay, start from based on our data set. This is the first data set is from January 1989. So the start here is C 1989 1, where the frequency is 12, because this is actually monthly data series. Right, so let's take a look at the originals, the plot here, the palm oil production graph. Okay, this is actually when we're talking about the original series, it means that we not performing any differencing method yet. Okay, so here for the original series, as we can see here, okay, the thing that you need to find in the pattern that you need to find in your original series is whether your data series has trend or not. Okay, for this case, whether our palm oil production have, okay, as we can see here, the pattern here is okay, when we plot the palm oil production against time, this particular chart show the series have some regular peaks here, okay, and trough here, regular peaks here. It means that there based on this plot, there is seasonal component. Okay, and then what we do, this is actually more on how to identify whether the data series need to do some differencing first or not before it turns into stationary. Okay, and then for this particular example, we know that we need to perform the seasonal differencing because there is actually seasonal component in the series, right? To confirm this particular observation, okay, we can plot the ACF and PACF, right? So for ACF and PACF, okay, when you see this wave-like pattern, okay, this wave-like pattern, especially peak for, okay, as we can see here, lag 12, lag 24, and so on. This is actually the pattern for where there is actually seasonal component in our series. Okay, when we plot the ACF, and even our PACF also show shows wave-like pattern, but it rather not obvious compared to ACF. Okay, so it confirm the series have seasonal effect. Okay, so what we do again, you refer back on how we plot the ARIMA model with seasonal component. Okay, so the thing that we need to investigate, okay, after that is, what if we perform the seasonal differencing? When we perform the seasonal differencing, is our series might become stationary or not? Okay, so for this particular example, okay, for the purpose of we can use this particular difference repeatedly. I assign this as palm oil c.ts. It means that for this particular object, it is a series that after we perform the seasonal differencing towards palm oil.ts. Okay, so lag equals to 12 here means that, okay, we want to perform the seasonal differencing. Okay, and then we can plot the series after we perform the seasonal differencing by calling the plot function, and we plot it towards this object, and then we will get this particular pattern. Alright, so obviously, even though that the seasonal component is not here after we perform, okay, it might suggest that the series is still not stationary. Okay, even after we perform, when we plotting the ACF and PACF for the seasonal differencing, okay, this palm oil CTS here, as we can see here, there are actually, okay, the slowly decaying pattern here, okay, decaying pattern, okay, here, and then even it still have some, okay, some wave pattern here. This is there are actually obvious pattern in your ACF. So, and for your PACF, as we can see here, there is one significant spike here. Okay, might suggest that we still need the non-seasonal differencing after we perform the first seasonal differencing. Okay, right, so here, as we can see here, again, what we do, okay, because I want to make it easy for you without, okay, without using the diff in this plot function, okay, I assign this particular object as non-c.ts. It means that this particular object we already performed the seasonal and non-seasonal differencing. Okay, here the function used is diff function, where the differences is equals to 1 towards the palm oil c.ts. Okay, and then we plot the series, we get this particular pattern, and as we can see here, now it seems that our original series is stationary. Okay, and we confirm it by plotting the ACF and PACF. Okay, right. So here, okay, for ARIMA with seasonal component, or we know it as SARIMA, okay, to identify the order of, okay, because we need to identify the ARIMA part, PDQ, the small capital, okay, and the seasonal part, okay, SAR, SMA, and so on. Okay, the way on how you determine the order of this particular spike is explained below. Okay, so here, after you perform the non-seasonal differencing, okay, we say that our series is now stationary. Okay, so here we stop at here. Okay, we stop at this, and now we take a look at the ACF and PACF to determine the order. So how can we determine? Okay, first, we know that we already performed the seasonal differencing. So the capital D is equals to 1. And then after that we perform the non-seasonal non-seasonal differencing. So the small capital D is equals to 1. Okay, so that's the thing. Now, how can we determine the ARP, the MEQ, the SARP, and the SMEQ? Okay, so here based on based on the significant spike here, we can determine the P and Q order. Okay, so for the SAR and SMAQ part, we look at lag 12 or 20, 24 or 36 for monthly data. Since that this is monthly, so we look at whether there are actually significant spike at lag 12 or 24 or 36. So based on how many spike in this particular lag, okay, it will determine our SAR and SMA. Okay, again, remember to read the SAR, the AR part is actually we take a look at how many significant spike at PACF, while MA is we take a look at how many significant spike at ACF. Okay, that's why to for SAR we look at PACF and at lag 12. Okay, 10, 11, 12. So this is one significant spike at lag 12. Okay, how about 24? Okay, so there is no significant spike at 24. So it means that the SAR order is P equals to 1. Okay, what about SMA? So SMA here we look at the ACF. Okay, so we look at 10, 11, 12. So this is one significant spike, barely touch the standard error band. Okay, so we can see that this is one significant spike at lag 12. So SMA equals to the Q order here is 1. Okay, and for another significant spike at lag, okay, at lag different than 12 or 24, this is how we read the the AR order and the MA order. Okay, you can read it based on this explanation, and based on the identification, we say that the most suitable model should be based on this is actually MA2, SMA1, AR2, SAR1. So it should be MA2. So based on this, it should be 212, 111. Okay, this is based on ACF and PACF. We identified it as the most suitable model. But again, like what we do in our previous example, we will try to figure out the best alternative to compare with this model. Okay, so the model that will be as an alternative is Sarima 112.011, Sarima 112.111, and Sarima 213.111. Okay, so how do we proceed with the next stage? Okay, model estimation and validation. Okay, so here we use the same ARIMA function, but instead of in addition with the order of the AR part, 212, we will add the seasonal part here. Okay, the seasonal part here 111, and we put 12 here to say that this is the Sarima 4 monthly series. Okay, the way on how to interpret it, it is actually the same as the CPI example. Okay, you just put the order here. Arima, the Arima part. Okay, and then the seasonal part, and then 12. Okay, so you can look at the example, and based on the lowest AEC, even though that we say for the first the first model is based on ACF and PACF, this is the best model, but when we compare with AIC, model 3 give us the lowest AIC, 2615. This is 2619, 2616. Okay, and then this is 2618. So this is the model that give us the lowest AIC. Alright, so I want to comment regarding this particular model model identification and estimation process and so on. Okay, sometimes we need to try and error. What are the best model that give us uh, the best that fulfill the the Prometheus test for the model. Okay, as we can see here, based on AIC, we choose model 3. So we will proceed the model application of model 3 after this. And then again we perform the Leung-Bok test. As we can see here, the p-value is greater than 0.05, which is we accept the null hypothesis of the residual are white noise. Okay, so next, after we choose this particular model, okay, we can forecast the value. Okay, we forecast the value. Okay, and then the value that we get is actually this. Okay, again, to forecast the value, we use predict function. This. Okay, this is we want to forecast value, the predict function here. Okay, and then we choose the model 3. Alright, and then what we do is we perform the 12 step ahead. Okay, I will organize this note back after this. Okay, I will put it in stage 3. Okay, right, so I hope that my explanation is sufficient for you to perform this analysis in your own. Okay, if you have any question, please ask me. Right, so thank you for listening. Bye.